There is a desert in Pakistan that has swallowed villages whole. It has buried roads beneath its sand. It has dried up wells that fed families for generations. It has pushed farming communities off land their ancestors cultivated for centuries, replacing green fields with drifting dunes and cracked clay that produces nothing. The Cholistan Desert in southern Punjab stretches across over 26,000 square kilometers of some of the harshest terrain on the Pakistani subcontinent. Summer temperatures exceed 50 degrees Celsius. Annual rainfall averages less than 150 millimeters. The groundwater is too saline to drink or irrigate with. And for the communities that survive at its edges, the desert has always represented one thing above all others: the end of possibility. But Pakistan made a decision, and the decision was this: dig a canal through it. Not a small irrigation channel, not a modest water supply project, a 500-kilometer engineered waterway, one of the longest new irrigation canals to be constructed anywhere in the world in the 21st century, designed to carry water from the Indus River system deep into the heart of territory that has been dry since recorded history began. This is the story of how Pakistan split half a desert to build a canal that changed their country forever. This is Quiet Tech Process. Pakistan's water crisis is not a future problem, it is a present emergency. The country supports a population of over 230 million people, making it the fifth most populous nation on Earth. It feeds that population primarily through irrigated agriculture, one of the most extensive irrigation systems in the world, built around the Indus River and its 5 major tributaries across the Punjab plains. But that system, largely constructed during the colonial era and expanded in the decades following independence, was designed for a Pakistan of 70 million people, not 230 million. The gap between water demand and water availability has been widening for decades. Per capita water availability in Pakistan has fallen from over 5,000 cubic meters per person per year at independence to under 1,000 cubic meters per person per year today, crossing the threshold that international water resource specialists define as water scarcity. Underground aquifers are being depleted at rates that far exceed natural recharge. Rivers run lower each year as glaciers retreat and seasonal rainfall patterns shift. And yet, across southern Punjab and northern Sindh, there are millions of hectares of land that could produce food. Land with good soil structure, adequate sunshine, and flat terrain ideal for agriculture, sitting empty and unproductive for one reason only: no water. The Cholistan Desert is the most dramatic example. Its soils, where tested, show considerable agricultural potential. The land is flat and workable. The climate, brutal as it is, can support wheat, cotton, and other major crops if water is provided reliably. For decades, Pakistani agricultural planners and water engineers looked at this potential and asked the same question: what would it take to bring water here? The answer they arrived at was ambitious, controversial, expensive, and technically demanding. It was also, in the assessment of the engineering teams that studied the problem most carefully, entirely achievable. Build a canal. The planning phase for the project began with surveys of a scale and thoroughness that the region had never seen before. Geotechnical investigation teams moved across the proposed corridor, drilling boreholes at regular intervals to characterize the subsurface conditions that the canal structure would rest on. Satellite imagery programs mapped the terrain in detail. Hydrological modeling teams calculated the water volumes available from the Indus system headworks that would feed the new canal, and the agricultural demand that the newly irrigated lands would generate. The corridor chosen for the canal route faced immediate engineering challenges of significant complexity. The terrain along the 500-kilometer alignment was not uniform. In its northern sections, the canal would pass through hard, rocky ground, requiring blasting and heavy excavation. Through its central reaches, it would cross sandy desert terrain, prone to wind erosion and requiring special lining protection.
In its southern sections, it would need to traverse areas of seasonal flooding, requiring elevated embankment construction and drainage infrastructure. The canal's design called for a trapezoidal cross-section with a bed width of 18 meters, side slopes of 1.5 horizontal to 1 vertical, and a design flow capacity of 6,500 cubic feet per second, enough water to irrigate over 1.2 million acres of previously unproductive land. The total earthwork volume required to excavate the canal prism across the full 500-kilometer alignment was calculated at over 180 million cubic meters. To put that number in context, it is more than twice the volume of material excavated during the construction of the Suez Canal. Construction mobilization began at multiple points along the alignment simultaneously. It could not be built sequentially from one end to the other. The 500-kilometer length made that logistically impossible within any reasonable construction timeline. Instead, the alignment was divided into construction packages, each managed by separate contractor teams working concurrently toward their neighbors. The first machines to break ground were the largest bulldozers in the Pakistani construction fleet. D-series dozers pushed the clearing operations across the alignment, removing vegetation, leveling surface irregularities, and establishing the preliminary platform from which the main excavation would operate. Behind the clearing machines came the excavation fleet, large hydraulic excavators working in combination with articulated dump truck fleets to cut the canal prism to design dimensions.
In the rocky northern sections, the excavation required drilling and blasting before mechanical removal was possible. Rock drilling rigs advanced across the excavation face in systematic patterns, boring blast holes to the specified depth and spacing. Controlled blasting operations fragmented the rock into manageable sizes. Then, hydraulic breakers on hydraulic arms reduced oversized fragments, and loading excavators filled the waiting dump trucks with broken rock material for haulage to designated disposal areas. In the sandy desert sections, the excavation challenge was different. The loose sand that was easy to dig was also prone to collapsing back into the excavated section before it could be protected. Engineering teams used temporary berm systems and managed excavation sequencing to minimize the exposure of excavated sand faces. The canal prism in these sections was excavated in stages, with the concrete lining operation following closely behind the excavation advance to protect the newly formed surfaces before they could be disturbed. The concrete lining of the canal was the single largest construction activity on the entire project. Raw excavated earthen surfaces cannot contain high-velocity irrigation water without severe erosion losses and leakage that would undermine the entire water delivery system. Every meter of the 500-kilometer canal needed to be lined, a continuous concrete surface covering the canal floor and both side slopes from end to end. The scale of concrete placement required was extraordinary. Specialized canal lining machines, tracked vehicles that move along the canal alignment on guide rails set at the design canal dimensions, placed and finished concrete in a continuous operation, advancing meter by meter as fresh concrete was pumped to the lining head. Concrete batching plants were established at regular intervals along the alignment to supply the lining machines with fresh mixed concrete within the workability window required for proper placement. The concrete mix design for the canal lining was specifically formulated for this application, a dense, relatively impermeable mix with good workability for the lining machine operation, adequate early strength to resist disturbance during the curing period, and long-term durability against the aggressive conditions of high-velocity water flow and the extreme temperature cycling of the desert environment. Expansion joints were formed at regular intervals in the lining to accommodate the thermal movement of a concrete structure exposed to temperature swings from above 50 degrees in summer to near freezing on winter nights. Miss these joints and the lining cracks. Crack the lining and the seepage losses undermine the canal bank. The precision of joint formation and placement across 500 kilometers of canal was a quality control challenge that required continuous inspection and monitoring throughout the construction program. At intervals along the canal route, major hydraulic structures were constructed. Head regulators at the upstream connection to the Indus system headworks controlled the intake flow into the canal.
Fall structures at elevation change points dissipated energy to prevent erosive velocities in the downstream reaches. Cross-drainage structures allowed natural drainage patterns to pass beneath or over the canal without disruption to either the canal operation or the surrounding drainage regime. Each of these structures was a significant concrete construction project in its own right. Reinforcing steel cage assembly teams fabricated the structural steel for each structure on site, cutting and bending bars to specification and assembling cages for crane placement into prepared formwork. Concrete pump trucks extended their booms to pour concrete into complex structural formwork systems. Engineers monitored the concrete placement continuously to ensure complete consolidation without segregation or void formation. The bridge crossing structures where public roads and tracks crossed the canal alignment required careful engineering to avoid disrupting either construction or traffic. Temporary diversions maintained road access during bridge foundation and substructure construction. Tower cranes lifted precast concrete beam elements into position across completed abutments and piers. Deck casting and finishing operations completed the crossing structures, which would eventually carry the traffic of farming communities accessing the newly productive land on both sides of the canal. As the construction advanced, the scale of the operation that had mobilized across the desert was staggering to observe. At peak construction activity, over 15,000 workers were employed across the full 500-kilometer alignment. Equipment inventories included hundreds of excavators, more than 600 dump trucks operating in continuous haulage cycles, dozens of concrete batching plants, and a fleet of lining machines advancing along the canal in multiple simultaneous work fronts. Supply chain logistics for this workforce and equipment fleet across desert terrain without existing infrastructure required construction of over 800 kilometers of temporary access roads, fuel supply facilities at regular intervals, and water supply systems for both human consumption and concrete production in territory where no existing water infrastructure existed.
The environmental conditions the construction teams worked in were extreme. Summer temperatures required special measures to protect both workers and fresh concrete from heat damage. Concrete placement at temperatures above 35 degrees requires ice addition to the mix water, insulated hauling equipment, and accelerated curing programs to prevent thermal cracking. Night shift operations during the hottest months moved a significant proportion of concrete placement to cooler hours. Sandstorms periodically shut down operations, required equipment protection, and added days to the construction schedule at affected workfronts. As the final sections of canal lining were completed and the structural works were finished and tested, the commissioning phase approached. Water control structures at the upstream headworks were prepared for first operation. Downstream sections of the canal were inspected and cleared of construction debris. Monitoring systems, flow measurement weirs, automated water level gauges, remote-operated gate control systems were installed and calibrated. And then the headworks gates were opened. Water from the Indus system, carrying the snowmelt of the Himalayas and the monsoon rainfall of a subcontinent, entered the new canal for the first time. It advanced along the concrete-lined prism, filling the trapezoidal section progressively from the intake toward the downstream end, testing every joint, every lining panel, every gate and structure along its 500-kilometer path. Engineers and inspection teams drove the length of the canal as the water advanced, watching for leaks, monitoring flow performance, checking structural behavior. The canal held. The structures performed. The water moved. The transformation that followed was visible within a single growing season. Farmers who had lived at the edges of the Cholistan Desert for generations found themselves with access to reliable irrigation water for the first time. Fields that had never been cultivated were plowed and planted. Wheat crops emerged from soil that had not produced food in living memory. Cotton fields appeared where there had been only sand. The green line of irrigated agriculture advanced into the desert as land was brought into production. The economic impact began accumulating immediately. Agricultural output from the newly irrigated land added directly to Pakistan's food production. New farming communities established themselves along the canal corridor. Infrastructure followed the water: roads, schools, health facilities, markets, the basic fabric of settled agricultural life building itself around the reliable water supply that the canal provided.
Over 1.2 million acres of previously unproductive land brought into production, hundreds of thousands of farming families with access to a water supply their predecessors never had. A desert that had been advancing, now stabilized at its margins by the vegetation and soil management that productive agriculture requires. Pakistan had split the desert, and the canal that ran through it had changed the country. Not just its landscape, its possibilities. This is what engineering does when it is applied at the scale the problem demands. This is Quiet Tech Process.